You know, when it is late June down in central Oklahoma and the thermometer outside is sitting at just like a blistering 102 degrees, there is really only one sound you want to hear when you walk through your front door.
Oh, absolutely. The steady, beautiful hum of your air conditioner.
Right. I mean, at that temperature, it is not a luxury anymore.
No, it's a matter of survival, or,
Yeah.
at least keeping your sanity when the humidity is just completely suffocating.
Yeah, exactly. So I want you to imagine being a homeowner in El Reno, Oklahoma.
Okay.
It's that exact kind of sweltering day. You walk inside expecting some relief, but the air is just thick, heavy. The house is basically a complete swamp.
Oh, no.
Yeah, the AC is totally dead, and naturally you have no idea why, right? So you call out a technician.
As you do.
Right.
Yeah.
They pull the access panel off the unit, they run their diagnostics, and they deliver a rather shocking verdict. They tell you that your system was killed by a violent thunderstorm.
Okay.
But here is the incredibly confusing part. There has not been a single cloud in the sky for 3 whole weeks.
Wow. I mean, it sounds like a mystery novel, but the culprit is entirely invisible.
Right.
And what the technician found inside that system really tells a whole story. When they pulled the control board out of the air handler, they saw that the heavy metal relay contacts were just, heavily pitted. Yeah, scarred with these tiny scorch marks.
Yeah.
And they also tested the microprocessor and found that it had been failing intermittently before totally giving up.
Interesting.
Yeah. And that specific combination of damage, that is the classic telltale footprint of delayed surge damage.
Okay, let's unpack this. Welcome to our deep dive into the source material today. We are pulling from the field data and the service notes of Hartzell's Heat and Air.
Right, a veteran HVAC company.
Yep, with 45 years of post-storm experience out in central Oklahoma. And our mission today is really to explore this hidden slow-motion destruction of modern heating and cooling systems.
It's a huge issue.
It really is. We want to figure out why brand new air conditioners are so fragile compared to the old clunky ones, how these invisible surges actually work, and most importantly, how you can prevent a massive repair bill.
Yeah, and it's a fascinating problem because the damaging power surges are almost always the ones you just never see coming.
Right.
Like when lightning hits a roof and blows a physical hole in it, right? Leaving a trail of melted wires and smoke. Well, the diagnosis is pretty obvious.
Yeah, a bit hard to miss.
Exactly. But these invisible surges operate on an entirely different level of physics.
So going back to our El Reno homeowner, we know the system limped along for 3 weeks after the storm.
Right.
How exactly does a machine get electrocuted by a massive spike in power, but not die instantly? I think a lot of us just picture like a cartoon lightning bolt instantly vaporizing whatever it touches.
Oh, for sure. That is the assumption. But let's look at the baseline mechanics of what is actually flowing through your walls. So a normal residential electrical supply, the power coming into your home from the grid, it runs at about 240 volts, which is split into 120 volt legs.
Got it.
Now, think of voltage like water pressure in a plumbing pipe.
Yeah.
You want that pressure to be incredibly consistent so your faucets work smoothly.
Right, because if the water pressure drops too low, you just get a trickle and nothing functions.
Exactly.
And if the pressure suddenly spikes to some extreme degree, the pipes literally burst under the stress.
That is the perfect way to look at it. A power surge is just a sudden extreme spike in that electrical pressure.
Wow.
And it usually only lasts for a few milliseconds. But in that tiny fraction of a second, the voltage can spike from a safe 120 volts all the way up to 600, 1500, or even higher.
That is massive.
It really is. Now, in the case of the El Reno homeowner, lightning actually hit a neighborhood utility transformer 2 blocks away.
Okay, 2 blocks away.
Yep. And it sent a massive 1200-volt spike rushing through the electrical grid and straight into their home. Crucially, their air conditioner was actively running right when that spike hit.
Man. And, reading through the field notes, lightning isn't even the only cause of these pressure spikes. Not by a long shot.
Not at all.
These massive surges can come from utility switching events, which is really just the power company rerouting electricity on the grid to balance loads.
Right.
They come from a transformer failing down the street. They even happen during those frustrating brownout events during a storm, when the lights dim, they flicker, and then the power just slams back on with a loud pop.
Oh, yeah. The restore part of a brownout then restore event is incredibly violent, electrically speaking.
Really?
Yeah, when the grid comes back online, the initial wave of energy is much higher than the baseline. Even large industrial equipment on your local grid just cycling on and off can push significant surges into your home's wiring.
So we had this environment where extreme high voltage can basically slam into the house from multiple avenues.
Precisely.
But returning to the mechanics of that slow death we were talking about, it sounds less like a knockout punch in a boxing match and more like a slow, undetected poison. The surge hits, but the machine keeps breathing.
Yes, and that slow poison leaves a very specific footprint over time. The data actually breaks down 3 distinct patterns of surge damage.
Okay.
The first is immediate failure. That's your knockout punch. A massive spike takes out a major component, the electrical pathways physically melt, and the system is just dead within minutes.
Okay, that makes sense.
But the other 2 patterns are much more insidious.
Right, the intermittent and the delayed failures.
Yeah. So intermittent operation happens when the surge partially damages a component. The AC works sometimes, maybe acts a little glitchy, and usually degrades over a few weeks.
That sounds frustrating to diagnose.
Oh, it is. But the delayed failure is where the slow poison analogy really shines. Imagine a heavy relay switch inside the system. The surge hits, and because of the excessive voltage, the electricity actually arcs across the gap. It leaves a microscopic scorch mark on the metal contacts. It also slightly weakens the internal insulation of the start capacitor.
Wow, so the system is technically still operating, but that tiny scorch mark acts like an infection.
Exactly.
Every time the AC turns on and that switch clicks into place over the next 3 weeks, the connection is compromised. It creates extra heat, stressing the surrounding components until the entire board completely gives out weeks later.
Yeah. And because of that 3-week delay, the homeowner never connects the failure to the storm. They just assume their equipment failed organically.
That makes total sense.
Right. But the technician arrives, sees the pitted contacts and the stressed microprocessor, and knows the real story.
Here's where it gets really interesting, though. Like, why are we talking about this so much now? Growing up, I feel like my parents had the same heavy, rattling metal box sitting outside their house for 30 years, and it survived everything.
Oh, they were built differently.
Seriously. Every thunderstorm, every power outage, every grid fluctuation. It never cared.
What's fascinating here is the sheer difference in the physical architecture of the technology from then to now. It is the classic paradox of modern engineering.
How so?
Well, if you look at an air conditioner built in the 1980s, it was practically a tractor. It had maybe 3 or 4 bulky electromechanical parts. You had a massive contactor, a capacitor, a heavy copper transformer, and a very basic thermostat that was essentially just a mercury switch.
Yeah, it's basically a tank. Those big, heavy mechanical parts and thick copper wires could absorb an immense amount of electrical abuse.
Absolutely.
I mean, a 1,500-volt spike might heat up a thick wire for a fraction of a second, but the system would just shrug off the heat and keep running as if nothing happened.
Exactly. Now compare that to a modern 2026 HVAC system.
Okay.
Today's units are effectively highly sensitive computers that also happen to pump refrigerant. We are talking about variable speed compressor inverters. We have smart control boards loaded with silicon chips. The variable speed blower motor inside has its own dedicated microelectronics. You even have a communicating thermostat that sends complex digital data streams back and forth with the main system.
Let's focus on those variable speed motors for a second, because I feel like that explains the vulnerability perfectly.
Yeah, okay.
An old motor just turned on or off. But a modern variable speed motor is constantly making micro adjustments to its speed to maximize energy efficiency. And to do that, it requires delicate logic circuits.
Tiny ones.
Right. We are talking about microscopic electrical pathways on a silicon board that operate on maybe 5 or 12 volts of power.
And that brings us to the core of the paradox. All of those dozens of modern solid-state components make today's systems vastly more energy efficient.
Oh, for sure.
They keep your home at a beautifully consistent temperature. They remove humidity perfectly. And under normal, everyday operating conditions, they are incredibly reliable. But if a 1,500-volt surge gets past the main power supply and hits a microscopic pathway designed for 5 volts, it doesn't just heat up. It instantly vaporizes the silicon.
Wow.
Yeah, we have traded the rugged durability of a metal tank for the high-performance precision of a glass cannon.
A glass cannon that sits plugged directly into the unpredictable electrical grid 24 hours a day, which honestly is terrifying if you just spend a small fortune on a new system.
It really is.
So naturally, as a homeowner, you start thinking about protection. And I know a lot of people listening are probably saying, hey, I'm covered. I pay my utility company for a surge protector.
Ah, yes. That is one of the most common and ultimately dangerous misconceptions we need to clear up based on the field data.
The meter protector.
Yes.
Many utility companies like OG&E down in Oklahoma offer a surge protector that mounts directly onto your electrical meter outside the house. They charge a nominal fee, something like $9 a month, right on your utility bill.
They do.
So I have to push back here. If I am paying my utility company every single month for a specialized surge protector, shouldn't my highly sensitive glass cannon AC unit be totally safe?
It is entirely reasonable to assume that, but the data tells a deeply frustrating story. According to the field notes from decades of post-storm repairs, that meter protector misses about 70% of HVAC surge damage.
Wait, 70%?
70%.
That is a massive failure rate for something you are paying a monthly subscription for. Why does it miss so much of the damage?
Because of its physical location and its design limitations. That meter device is really only a first line of defense.
Okay.
It catches the absolute biggest, most obvious spikes coming in directly from the external grid. But it cannot catch the residual spikes, the extra wave of voltage that slips past the device in the milliseconds before it fully clamps down.
Right.
And even more importantly, it is completely blind to surges that originate inside your own house.
Yes. I found that detail in the source notes fascinating. Surges come from inside the house.
All the time.
Every time a major appliance with a large electric motor cycles on, like an older refrigerator compressor kicking in or turning on a heavy-duty vacuum cleaner, it demands a massive draught of power and can send a mini surge rippling backward through your home's wiring.
Exactly.
That internal surge travels through the walls and goes straight to your air conditioner's delicate control board, completely bypassing the utility meter outside.
Yeah, the utility meter protector is basically a bouncer standing at the front door of a nightclub.
Okay, I like that.
He is great at stopping the massive, obvious threats from coming in off the street. But he is letting a lot of residual rowdy behavior slip by him, and he has absolutely no idea what is happening inside the VIP room where your sensitive electronics are sitting.
That is such a good analogy. And that is why the industry professionals, the people actually in the field replacing these burnt-out boards, strongly recommend a layered defense.
Yes, a three-tiered shield.
Exactly. Let's break that shield down, because this is the actual mechanical solution to the problem. The sources point to Tier 1 being the panel protector.
Right.
This is a device mounted directly onto your main electrical breaker panel. It catches everything coming through the service entrance. The National Electrical Code, specifically the NEC 2020 update, actually mandates these Type 2 protectors on all new residential construction.
Right, so if you have a recently built home, you likely have Tier 1 in place. If you have an older home, an electrician can retrofit one onto your panel for about $300 to $600.
Okay.
But as we just established with the bouncer analogy, the panel protector still isn't enough on its own to protect the glass cannon. It is too far away from the actual equipment.
Which brings us to Tier 2 and Tier 3.
Yep.
Tier 2 is the outdoor equipment protector. This is a dedicated, specialized device installed right at the outdoor disconnect box, mere inches away from your AC compressor.
Super close.
And Tier 3 is the indoor equipment protector, installed directly at the indoor air handler, or furnace, to protect that variable speed blower motor.
Yeah, and the mechanics of how those equipment-level protectors function is just a brilliant piece of engineering. The field notes highlight reliable brands like Intermatic, Eaton, and Square D.
Yeah.
Inside these devices are components called MOVs, which stands for metal oxide varistors.
Okay, and think of an MOV like a high-speed pressure relief valve on a boiler.
Perfect comparison.
When the electrical voltage is normal, at that safe 120 or 240 volts, the MOV stays completely closed. It just watches the power flow smoothly to the AC unit.
Right.
But the absolute millisecond a massive voltage spike hits the line, the MOV detects the dangerous pressure. It instantly opens up, clamps the voltage down to a safe level, and forcefully redirects all that excess destructive electrical energy away from your AC and dumps it straight into the earth through your home's ground wire.
It's amazing. They are incredibly robust. A high-quality MOV can handle an unbelievable amount of energy redirecting up to 50,000 amps of surge current safely into the ground before it can cross the threshold into your control board.
50,000 amps.
Yeah, And because you place them right next to the outdoor compressor in the indoor unit, they catch the internal surges from your refrigerator, they catch the residual grid spikes that got past the electrical panel, and they stop the damage literal inches before it vaporizes your microprocessors.
Wow. So we understand the vulnerability of modern tech. We understand how the invisible enemy works, and we know exactly how the MOV shield functions.
Yes.
But let's be real for a second. Asking someone to spend hundreds of dollars on preventative electrical equipment before a storm even happens is a tough sell.
Oh, absolutely.
Human nature just hopes it won't happen to us. So we really need to look at the financial math of what happens when you roll the dice and lose.
Well, to accurately calculate that risk, we really have to separate a direct lightning strike from a phenomenon called near-strike induction.
Okay, let's start with a direct hit. That is the apocalyptic scenario. That is when lightning physically strikes your roof or your chimney. It is devastating, but statistically, it is quite rare. If that happens, you are looking at $8,000 to $25,000 in damage across your HVAC, your major appliances, your electronics, and likely structural damage to the home itself.
Oh, yeah.
And let's be very clear based on the engineering data. No surge protector on the consumer market will stop a direct lightning hit. The sheer volume of energy is simply too massive. It will just arc right over the protector and melt everything.
Exactly. But the real everyday danger isn't the direct hit. If we connect this to the bigger picture, near-strike induction is 100 times more common than a direct lightning strike.
100 times.
Yeah. This occurs when lightning strikes a large oak tree down the street, or a telephone pole a block away, or even your neighbor's house.
So think of near-stroke induction like dropping a massive boulder into a calm pond.
Right.
The lightning is the boulder. It doesn't have to physically hit your boat to capsize it. When that bolt hits down the street, the sheer power creates a massive wave of electromagnetic energy that ripples outward.
It's invisible, but it's powerful.
Exactly. When that invisible magnetic field washes over your house, it interacts with the copper wiring hidden inside your walls. The magnetic wave physically pushes the electrons in your wires, inducing a massive, instantaneous 1,500-volt surge of electricity inside your home.
The lightning never touched your property, but the electromagnetic wave just spiked the power running to your air conditioner.
Wow.
And that induced surge is exactly the type of event that equipment protectors are perfectly designed to intercept and neutralize. If you don't have those protectors installed, you fall straight into a remarkably painful financial trap.
Okay, let's talk about that trap. Imagine this scenario. The storm rolls through, the induction surge hits. Your system dies 3 weeks later.
Just like El Reno.
Exactly. You get the repair quote from the technician and think, no problem, I just bought this top-of-the-line Train or Mana system 2 years ago. I have a 10-year parts warranty.
Yeah, you'd think that.
But denied. If you read the fine print in the service literature, manufacturer warranties explicitly state they do not cover damage from what they categorize as external causes.
Yeah.
A power surge is an external electrical event, so your warranty is completely voided for that repair.
It's brutal. So you pivot to your backup plan, right? You turn to your homeowner's insurance policy,
Right.
which introduces a secondary layer of frustration. The vast majority of standard homeowner insurance policies carry a deductible ranging from $1,000 to $2,500.
And let's run the actual repair numbers from Dave Hartzell's service calls to see why this is such a nightmare for the homeowner.
Let's hear it.
Say the induction surge fries the outdoor control board. Replacing that single part runs $400 to $700.
Okay.
If it takes out the indoor board, that adds $350 to $600. If it hits that variable speed blower motor module we discussed, you're looking at $600 to $1,200. And if it kills the sophisticated inverter driver on a high-end system, that is an $800 to $1,800 repair.
Ouch. Furthermore, those specialized solid-state parts are getting increasingly difficult to source quickly. You might be sitting in a 102-degree house for 4 or 5 days just waiting for a specialized board to ship from a warehouse.
That sounds miserable.
It is. In a worst-case surge scenario, multiple components are taken out simultaneously, easily pushing the repair bill to $3,000.
But let's look at the most common moderate scenario. The surge kills the inverter driver board. The total repair bill comes to $1,500.
Right.
You are trapped. The manufacturer's warranty won't pay for it because it was an external power surge. Your homeowner's insurance won't pay for it because the $1,500 bill is below your $2,000 deductible. You are left writing a check for $1,500 entirely out of your own pocket for a storm you don't even remember happening.
That is an agonizing realization.
Literally.
So we have to look at the upfront investment required to prevent this entire scenario. Dave Hartzell recommends that for any highly sensitive modern system under 10 years old, you absolutely must install the protection stack.
The three-tier shield.
Exactly. The equipment-level protectors, the MOVs installed right at the outdoor compressor and the indoor air handler, cost about $250 each, fully installed by a professional. That is $500 to secure the HVAC system.
And if you live in an older home and need an electrician to retrofit the main panel protector, that is roughly another $450. So for a comprehensive three-tiered defense stack protecting the entire house, you are looking at an investment of about $950 total.
Yeah, and we have to balance that against the statistical reality of the grid. The engineering data shows that a typical residential home experiences one major, potentially damaging surge event every 7 to 10 years.
So you spend $950 one time for a lifetime of protection to avoid a recurring $1,500 out-of-pocket hit every decade. Exactly. The mathematical logic is undeniably in favor of prevention. You are securing a delicate piece of machinery that costs as much as a reliable used car.
It is the definition of a necessary investment. Leaving these modern microprocessors exposed to raw grid fluctuations is a gamble where the statistical odds are heavily stacked against the homeowner.
So what does this all mean? Let's bring everything we've covered today into focus. If there was one core takeaway for you today, it is this. Your beautiful, quiet, high-efficiency modern HVAC system is not the rugged metal tank your parents had.
Not at all.
It is effectively a highly sensitive, uninsured computer that is plugged directly into an unpredictable and sometimes violent electrical grid.
Think back to the El Reno homeowner. They were forced to pay hundreds of dollars out of pocket while sweating through a 102-degree afternoon, all because an invisible magnetic wave from a lightning bolt 2 blocks away slowly cooked their control board over the course of almost a month.
Such a frustrating situation.
Spending a relatively small amount of money up front to install MOVs prevents a massive, agonizing headache down the road.
And it is worth noting that the professionals in the trenches take this incredibly seriously. Hartzell's Heat and Air, who service Kingfisher, Canadian, Garfield, Logan, Blaine, Major, and Northwest Oklahoma counties, consider this threat so severe that they refuse to install a new HVAC system without integrating equipment-level surge protectors.
Wow.
Yeah, it is their mandatory standard practice. If you live in their service area and want an assessment of your home's vulnerability, you can actually reach them directly at 405-375-4822.
Good to know. But before we wrap up our deep dive into the source material today, there is one final lingering implication from the physics of these surges that really deserves some critical thought.
Okay, what is it?
We have spent this entire discussion establishing the mechanics of near-strike induction. We know that this invisible electromagnetic pulse can silently travel through your walls, easily bypass your utility meter, and slowly chew up a heavy-duty 240-volt air conditioning unit over the course of 3 weeks.
Right. And here's the provocative thought that should probably keep you up at night.
Oh, boy.
If these invisible 1,500-volt spikes are quietly degrading a robust, major appliance like a central air conditioner, what on earth are they silently doing right now to the delicate microprocessors in your smart fridge, your expensive OLED television, and all the other sensitive devices plugged directly into the unprotected walls of your home?
Oh, wow. It forces you to look at every single outlet in your house through a completely different lens, doesn't it?
It certainly does. We will leave you to think on that. Stay curious, stay well-informed, and maybe go check the fine print on those warranties. Until next time.